Okay, so I'll be starting off with X-ray spectroscopy, and we are going to be looking at the different um, analytical techniques under X-ray spectroscopy. Noteworthy is the fact that this lecture is going to cover X-ray spectroscopy. It is also going to cover polarimetry and um, refractometry. Now, straight to X-ray spectroscopy. For X-ray spectroscopy, we will center in on X-ray emission spectroscopy and X-ray fluorescence spectroscopy. So those are the two methods we are going to consider. Yes, there are other methods, but these methods um, can okay. We're also going to consider XRD. Yes, under the X-ray methods. Yes, there are other methods like the EDX, where we have energy dispersive X-ray, okay, and the XPS, that's X-ray photo electron spectroscopy. Now, let's go straight into X-ray spectroscopy. So, X-rays. So, to talk about X-ray spectroscopy, of course, you have to talk about X-rays. So, X-rays are electromagnetic radiation ranging in wavelength from 0.1, okay, you can see there, to 25 angstroms. 0.1 to 25 angstroms. Now, the shorter the wavelength of the X-ray, the greater the energy and the greater its penetrating power. Remember, based on the equation E is equals to hc over lambda, we know that energy is inversely proportional to wavelength. So when the wavelength is long, the energy is low. When the wavelength is short, the energy is high. Okay. Now, both light and X-rays are produced by electronic transitions. Yes. So light, that's both visible light and UV light, produces electronic transition, as we have considered under spectroscopy with the BSc chemistry students. Okay. However, there's a difference between the kind of electronic transition that goes on with light and with X-ray. With light, the transition involves the outer electrons, but with X-rays, the transition involves the inner electrons. Okay. Now, X-ray spectroscopy is concerned with the measurement rather, with the measurement of the absorption of X-rays. So we are looking at the measurement of the absorption of X-rays when it interacts with matter. When it interacts with matter. So that's the introduction. You can skip the objectives. So, and then on to the definition. Yeah, so like we said, X-ray spectroscopy is a technique which involves the study of the interaction between X-ray radiation with matter. Now to the sources of X-rays. So these are the common sources: electron bombardment of a metal target, to irradiation of a target. So the first one is you have a metal target, okay, you have a metal and then you bombard it with electrons to produce X-rays. The second one, simply put, is the second one, you are producing X-rays from X-rays, okay, that is the second one. So you have a sample, okay, and then you irradiate the sample with a high energy X-ray to produce a secondary beam of fluorescent X-rays. The third one is actually quite sensitive and rarely used in an ordinary laboratory. However, it involves the use of a radioactive material. So you must have a radioactive source, okay, and then you expose a sample to it, and then it generates X-rays. So that is the third one. So take note of this. So you just need to outline the sources of X-rays under this section. You might not, you can just read this up on your own. Now we move to the spectrometer. Okay, that's X-ray emission spectrometer. Now this is a device or instrument used to measure analytically the emission of the X-ray radiation by a sample, right? Now the instrument consists of the source, the specimen chamber, the collimator, the crystal analyzer, auxiliary collimator, and detector. Now take note of this block diagram. Okay, take note of the block diagram. So the block diagram involves the X-ray tube, specimen, collimator, crystal analyzer, auxiliary collimator and detector. So what happens here? The X-ray is produced, okay, in the X-ray tube and then passed through this specimen. But because it is still in a very scattered form, the collimator reduces the scattering, narrows the X-ray, and passes it through the crystal analyzer. You can see the crystal analyzer, and then it passes through the collimator, okay, to further narrow it down, and then the X-rays are passed to the detector. So that's what you have there. Now we have different types of crystals used. Yes, so you can see it here, crystals. Okay, you can follow my cursor. Now crystals commonly used are topaz, lithium fluoride, sodium chloride, ammonium dihydrogen phosphate ADP, ethylene diamine D tartrate, etc. So take note of these crystals. Okay, take note of the crystals used. Next, we look at the types of detectors that are used. Okay, types of X-ray detectors that are commonly used, and the simplest one is, that's the first one, is a photographic film or plate. The second one, gas ionization detectors like ionization chamber, proportional counters, and the Geiger tubes. Number three, crystals that fluoresce. Okay, crystals that fluoresce in the UV or visible region when exposed to X-rays can also be used as X-ray detectors, right? So these are the three types. In case you are asked in a test or exam condition, you should know how to put this down. Now, this is another diagram you should get used to. Okay, here you have a non-dispersive X-ray spectrometer. So how is this different? This is a simpler method, okay? This is a simpler setup. However, and less just not that costly, so it's relatively cheap or and but the issue you are going to get here is the resolution. It gives a poorer resolution. So you can see where the X-ray comes in, then you can see where you place the sample below, and then it moves it to the detector. So okay, take note of that diagram. Now we move to application. So different types of solids are used. Okay, so and this is commonly used in the analysis of steels and alloys. So you can tell you, okay, this your steel is made up of this. You understand, because the composition of steel, for instance, determines the strength, the kind of application you can use it for, and all of that. So steel and metal alloys, and for the determination of heavy elements in organic samples. You want to find out whether, okay, soil is contaminated, or you want to find out whether you want to analyze aviation fuels, okay, like we have seen. So these are things you can use it. That's a wide range of application. Next, we move to X-ray absorption. Okay, but I wouldn't want to, I'll just be quite specific and move down to X-ray fluorescence. So you can read this on your own. So Now, X-ray fluorescence. So X-ray fluorescence is another method still under the X-ray methods. And the X-ray fluorescence spectroscopy is used for elemental analysis. It is a non-destructive method for elemental analysis. So you want to find out the elements present in a sample, like cement, for instance. This is commonly used in the cement industry. Okay, it is used in the mining industry. Okay, it is also used in artifact industry where you sell precious substances and all of that. So, and even in forensic, so maybe you are trying to detect maybe crime detection and all of that. So, this is an important analytical technique. Okay, so that's X-ray fluorescence spectroscopy. So, take note of the applications here. Okay, so you can read up. Now, yes, we move to another type next. Okay. So now here we are going to be looking at the X-ray diffraction. Okay, good. X-ray diffraction. So X-ray diffraction, we are looking at the X-ray, okay, coming in contact with the crystal, and when it comes in contact with the crystal, it is diffracted at different planes of the crystal. Okay, so the layers of atoms in a crystal act as the diffraction grating for the X-rays. So with this, you can know the type of crystal that is, because different crystals have different diffraction patterns. Then different crystals have different position of their peak. So we are going to look at that. I'll bring a sample um, diffraction pattern to class, and then we consider it and see how we can use it for analysis. Okay, this is especially important because I remember my student who had to help or assist a geological team in deciphering or interpreting the XRD data. It was just in, I think, 300 level then, so it's something you need to know. Now, X-ray diffraction is a phenomenon in which the waves of X-rays spread and bend as they pass through small openings or around barrier. So now for the diffraction, X-ray diffraction, okay? So we've talked about X-rays, right? So, but when the waves pass through crystals, this is the line I want you to look at. When the X-rays, so when the waves pass through crystals, they diffract. So that means they form interference patterns. So these patterns can be analyzed to gain information about the geometric structure and properties of the crystals. So take note of this. Now we are looking at the X-ray diffraction. I just want you to take note of the very important aspect. So this is a simplified diagram of scattering of X-ray by crystal. So you see the X-ray, okay, and then it scatters the X-ray. So the scattering is not just anyhow; it follows some patterns, okay, and that is the basis of our measurement. So I'll quickly move to Bragg's equation, okay. So this diffraction follows the Bragg's equation, and there you have the Bragg's equation. N lambda is equals to 2d sine theta. N lambda is equals to 2d sine theta. So let's see how we can use this. I can give you something like this in an exam or test condition. Okay. Now, example, when X-rays of wavelength 1.54 times 10 raised to power minus 8 centimeters passed through sodium chloride, an intense cone is formed at theta is equals to 15 times 0.87 degrees. If this is taken as first order reflection, then so here we want to calculate the interlayer spacing. Okay, so with the XRD, you can determine interlayer spacing, you can determine crystallite size, okay, and some other information. You can determine the crystalline phase, okay. In some instances, you can even determine the purity of the crystal, right? In some instances, you can determine the oxide, kind of oxide, you have metal oxide. So it's used for many applications. But let's look at interlayer spacing. So in this case, you are calculating interlayer spacing, and you see that's D here. So you make D the subject of formula, and then you get your answer, right? Okay. Now to applications. So I've talked about the applications already. So many applications that are not even mentioned here. Okay, but another important one is XRD led to the discovery of double helical structure of DNA. You know how important that is. Okay, when you're talking about life, you're talking about, so in fact, the gene, chromosomes, and yeah, so this is a very big deal. Okay, so XRD led to the discovery of the double helical structure of DNA. So we move to our next technique. Okay, now to our next technique, that is polarimetry. Now, polarimetry is the method of analysis which is based on the ability of a given compound in solution to rotate a plane polarized light to a certain direction. Okay, so you can look at the diagram below. Yes, so this is your ordinary light, and here you can see that it is oscillating in random directions every day, but here you can see the next diagram here where it is resolved, right? So it is properly resolved, and so the light, so it has its own plane, right, in two different directions. So you can see two different directions, this and this. Okay, so that is what it means. Now, it is possible for a crystal to rotate the plane of polarized light. Okay, you can rotate this way or rotate that way. So that is what we are going to look at. Okay, so the extent to which crystal or a substance or sample can rotate. Now let's move on. Yes, so an instrument used in measuring the optical rotation of a substance in solution is called a polarimeter. Okay, and the phenomenon is called polarimetry. Now, some compounds in solution have the power of rotating the plane polarized light to a certain direction, so it can rotate it. Now, such compounds are said to be optically active, and then in organic compounds you can find one or more asymmetric carbons within the molecule. So I'm sure you know what asymmetric carbons are. That's a carbon atom with four different substituents. Okay, so that is asymmetric carbons within the molecule. So that is important for organic compounds to be optically active. Now, that is why if you hark back to your organic chemistry, you might remember the concept of dextrorotatory, that's plus, or levo rotatory, and that's minus. So this is where it is now applicable. Okay, take note of this: the extent to which a sample can or the sample can rotate the plane polarized light is dependent on different conditions. So these are the conditions we'll be looking at. The nature of the compound itself, right? Then the nature of the solvent you are using for that experiment. Third, the depth of the solution through which light passes. Importantly, this is of great importance, the concentration of the solution, the temperature, and the wavelength of the light used. So these all affect the extent of the degree of rotation of the plane polarized light. So normally the wavelength of light that is used is the sodium D line, which has a wavelength of which is 589.3 nanometers. And the temperature for measurement is usually 20 degrees Celsius, but instruments for sake of ease of measurement and all of that, and because we're in the tropics, so usually you find 25 degrees Celsius. So okay, now you can read this up the prism. I'll just go straight to the diagram. Okay, so here you have the diagram, right? So you can follow my cursor. The light comes in. Remember, the light has a specific wavelength. You have condensing lens. You have the polarizer nickel. Okay, you have the quartz plate, right? And then it goes through. Now, the polarimeter tube, in the middle, you have your sample. Around it, you have water. Okay, and sample. Then this is your analyzer nickel. This is where you have to adjust this, okay, to ensure that it matches the light on both this thing, that's um, the direction of the light, okay, matches each other. So you adjust with this is the analyzer nickel. You have this already. So you adjust it, okay. So when you now pour in your sample, it will change. And once it changes, you will readjust it again. So that adjustment gives you the angle, okay, it gives you the degree, and it is that degree that you need. It is that degree that you need. Okay, so that is how the instrument is used. But you can read up, okay, you can read up from this and um get further deeper understanding of the process. Now um let's look at some small uses of polarimeter. So uses of polarimeter. Before then, I think, okay, yes, we talked about this. So the polarizer. So the polarizer is what you use to assemble the that's what you use to polarize the incident light. Then you have the polarimeter tube. Then you have the analyzer. That's the nickel prism. Okay, and all that. So those are essential parts out of the whole lot. Now, uses of polarimeter. Okay, what's the use of course, you can determine the angle of rotation, right? Then another important one is you can use it to identify an optically active substance of known concentration. Next, from the optical rotation of mixed solution of two substances, okay, for instance, sucrose and glucose, you can know their concentration, their respective concentration. That means you have mixed sucrose and glucose, right? But with a polarimeter, you can know the concentration of sucrose and also know the concentration of glucose. That is possible. Okay, so then you can also determine the concentration of the solutes, okay, in solution. So that can be done too. Okay, you can determine the concentration of a solute in solution if the specific rotation of that solute is already known, right? So those are the applications of polarimetry. Okay, now another important technique, and the last one for this lecture, is refractometry. Refractometry. For refractometry, we are looking at a concept in physics which is called refraction. So refraction, when light passes from one medium to another, it bends. I'm sure you'll have seen it in movies and all that. It bends. Okay. So it's just like I remember there was a movie I watched some time ago, and the light entered into the stream. Okay, but you could see the light coming from an angle, okay, that's outside the stream, but on entering the stream, very clear, is it a stream, or I think it's a stream or a lake. I think it's a lake. So it's a lake. So on entering the lake, it bends. Okay. And it's steeper. Okay. The light is steeper as it enters the lake. So I'm going to see that example here. Okay. So here's an example. So you can follow my cursor. So here is the incident. Let's assume below here is the lake. The light comes in and it bends. Okay, you can see how it. So this is outside. It comes in and bends. But like this example is talking about air and glass too. So it can happen between air and glass, air and water, air and different solvents, right? But what must happen is there must be a change in medium, right? You must change medium from something to somewhere. So there must be a change in medium. It can be a solvent and glass too. It's not always air. Okay, so take note of that. So, but you will notice that there's a bending, and that's what we call refraction, right? And take note of these angles. You have Q1, you have Q2. So you have the incident ray. That's the one coming from the first medium. It's called incident ray. Then after refraction, you call it refracted ray. Okay, refracted ray. Now that's the concept of refraction, right? Refractometry is a method which measures the refractive index of a substance. Now, the refractive index measures the angle at which a light ray will be bent when passing from one medium to another. Now, I've already explained the concept behind, but part of what you can read this, it's the density of the medium changes, and then it affects the, so you can read it up. Okay, but this is what I want you to take note of here, is the basic formula for refractive index. So here you have velocity in air over velocity in medium. Here you have the sine of the angle, incident angle, okay, over sine of the refractive angle. So that is what you have here. Okay. Now, so how to calculate the exact refractive index? So generally, as you said earlier, so literature values, you can actually get the value for the so for the D line of the sodium lamp, that's 589.3 nanometers at 20 degrees Celsius. However, we know that our experiments will be performed at temperatures other than 20 degrees Celsius, and that is why there's a need for this correction factor we see here. Okay, ND for 20, that's refractive index 20 for D line, right, is equals to N observed plus this 0.00045 then times T minus 20. So now let's use it to solve problem. So a student measures the refractive index of an organic liquid. The value obtained at 18 degrees Celsius is 1.2821. What is the corrected refractive index? So look up. Now, this corrected refractive index is what we want to determine, right? We have our observed, we know the temperature, and then you input your values, and then you get it here, 1.28. 18. So that is the value. Okay. Now, I wish we could do a demonstration how I wish, because this is something I've used and I really love using it because I use it to analyze soft drinks. So it's also used in some companies to analyze their beer, their wine. In the food industry, it's commonly used. In fact, you have the handheld refractometer, but a common one is the Abbey refractometer. That is the industry standard, I think. I want to believe that is still so till now. Abbey refractometer. Okay, so taking note of that, you can read it up, but you know, seeing is believing, and that also helps to um immerse it in your mind. So if I can visit any laboratory and use it, I will do a demonstration for you. That is time dependent. So now, um we know that we want to get the refractive index. Okay, so there are different, for different liquids there are different refractive indexes. So you can see acetonitrile, hexane, propan-1-ol, butan-1-ol, cyclohexane, toluene. So these are the refractive indices, okay, of all of them. Now, but like I said, application is a big deal here, right? So application is a big deal for refractive index, yes. So application. So application refractometer is essentially an analytical instrument used to determine the composition of binary mixtures or to determine the purity of compounds. Like those making alcohol, okay, they use it to determine the quantity of sugar, okay, because some of these alcoholic drinks are made from sugary or sugar, even some pure sugar, right? Now, so you want to know how fast the sugar is being converted to alcohol, for instance, okay, or you are concentrating sugar to form syrup, or you are making a fruit concentrate, for instance. No, fruit concentrate and all of that very expensive now. No, so if you can find a company to supply, you are in money. Okay, so food concentrates and all that. So in addition to this, refractometry can be used to estimate molecular weights, molecular sizes and shapes, and to calculate properties such as reflectivity and optical dispersion. Okay, so it has wide applications, but as I told you, the food industry is a very common analytical technique in the food industry. In fact, some people are employed just because of this. They handle these are kind of analysis in the industry. So yes, so with this we come to the end of this lecture. So I'll continue from here in my next class.